morning everyone. Today we are going to see operating system unit 3 session 10. In the previous session we have studied producer consumer problem and reader writers problem of process synchronization. In this problem there is a circular table surrounded with 5 chairs and there are 5 philosophers sitting on each chair. In front of each philosopher there is a plate of noodles. So there are 5 plates of noodles in front of each philosophers. And there are 5 chopsticks in between the philosophers. So these chopsticks are used to eat the noodles, but there are only 5 chopsticks. So if a philosopher wants to eat, he has to use the left chopstick and right chopsticks. Then only he can able to eat it. But there are not enough chopsticks available for all the philosophers to eat at a time. So they have to share these chopsticks among each other and they have to eat it. So they have to share the chopsticks in such a way that all the philosophers must get to eat. So when a philosopher is eating, the other philosopher, that is the neighbor philosophers, has to think. So this is one way for synchronization. When one philosopher is eating, the other philosopher, neighbor philosophers, has to think. And when that philosopher finishes eating, then the neighbor philosophers can eat. So like this way, the synchronization must be done between the philosophers and the chopstick so that they can eat and think. So a philosopher can eat noodles only when he acquires both left and right chopstick. On the left, a philosopher can pick the chopstick that is between him and his neighbor. And similarly on the right, he can pick the chopstick that is between him and right neighbor. So if this philosopher wants to eat, he has to pick left and right chopstick. Each chopstick can be used by only one philosopher at a time. Means a philosopher has to wait for chopstick until it is free. After eating, philosopher has to put down both left and right chopsticks and go back to thinking. So the chopsticks are free and it can be used by other philosophers. So here philosophers are processes and chopsticks are shared data. So these philosophers are processes and these chopsticks are shared data shared among philosophers. So the problem is to design a solution in a such a way that mutual exclusion among philosophers is there. That means when one process is eating, the other neighbor process has to wait until that philosopher finish. And also no philosopher should starve to acquire and not to wait for long time for chopsticks. So these conditions must be taken care. Philosophers must be not allowed to wait for a long time and mutual exclusion condition has to be met between the philosophers. No any clashes should happen. Synchronization must be proper. So there is a dining room containing a circular table with 5 chairs. There are 5 philosophers sitting on chairs and sharing a circular table. In the middle of the table there is a bowl of rice or noodles. For each philosopher there is a plate and between each plate there is a single chopstick, means chopsticks are placed between each pair of adjacent philosophers. Philosophers can either eat or think, cannot do both the things at the same time. When a philosopher wants to eat, he uses 2 chopsticks. When a philosopher wants to think, he keeps down both the chopstick. On the left, a philosopher can pick the chopstick that is between him and his left neighbor, and on the right, a philosopher can pick the chopstick that is between him and his right neighbor. So here philosophers are processes and chopsticks are shared data. The problem is to design the mutual exclusion among philosophers and no philosopher should starve to acquire for chopstick. So these chopsticks and philosophers are arranged in this way. Now there are 5 philosophers. P1, the second, this is, let us take this is P0, P1, P2 and P3 and P4. So 5 philosophers, and in between we have here chopstick, chopstick 0, chopstick 1 and chopstick 2, chopstick 3 and chopstick 4. So if process P4 wants to eat the chopstick, has to acquire the left chopstick 0 and the right chopstick 4. Then the processor P4 can eat. So this is the algorithm for dining philosophers problem, where chopsticks are initialized in an array from 0 to 1, from 0 to 4, and all are initialized to 1, and the processes are named like process 0, 1, 2, 4, as there are 5 philosophers. So the philosophers are going to execute the wait operation to acquire left chopsticks. So this acquires left chopstick, and this wait operation acquires right chopstick. So whatever the I value is, if the I value is 0, that means process 0 it is. If the I value is 1, then it is process 1. If the I value is 2, then it is process 2. So they have to acquire the left chopstick, and this is for right chopstick. Now suppose if the process is P4, that means here I value is here 4. I value is 4 here. So this I is equal to 4. So fourth process is going to acquire the fourth process chopstick, and see now I value is 4 here. 4 plus 1, 5, modulus 5. So 4 plus 1 it is. 4 plus 1 modulus 5. So 4 plus 1 it is 5 modulus 5. We get the modulus here 0. So the process 4 is going to, now here this is the process 4. Process 4 is going to acquire the 0th position chopstick and the 4th position chopstick. This is the left and this is the right. So like this way, the philosopher's neighbors, he's going to acquire the it, and once they acquire the chopstick, they are going to eat it. That process, philosopher is going to eat it, and then after finishing, the philosopher is going to release the left chopstick, and the philosopher is going to release the right chopstick, and then again they are going to start thinking so that neighbors can use the chopstick for eating. What problem arises in this algorithm is, at the same time, if all the philosophers try to pick up the chopstick at the same time, then all processes are going to stuck there. None of the philosophers or the processes will get the chance to eat the noodles, because all the philosophers have picked up the chopsticks at the same time, and those all are stuck now. Nobody can eat. We can see this in the video.
Of dining philosophers problem. 5 philosophers gather for dinner. They sit at a round table with their bowls of rice. A philosopher can either think or eat. For eating, a philosopher must have 2 chopsticks in their hand. The problem is, though there are 5 bowls of rice for each philosopher, the chopsticks are placed between each pair of adjacent philosophers. As you can see, this philosopher picks up 2 chopsticks and have his bowl of rice. After he is done with eating, he has to place back the 2 chopsticks in their place and continue to think. Let us see how deadlock is possible in this case. Each philosopher will pick up one chopstick that is adjacent to him. In this case, every philosopher will have one chopstick in their hand and will be waiting for the second chopstick, because a philosopher will need two chopsticks to eat his bowl of rice. So every philosopher will have one chopstick in their hand and will be waiting for the another chopstick that is held by another philosopher. So this is a deadlock condition. Everybody is having one resource and is waiting for another philosopher to release the resource. This is an example of deadlock.
So the solution to this problem is allow philosophers to sit and think at once. Allow philosophers to pick up both chopsticks if available. Otherwise, don't allow a single chopsticks to be picked. So if both are available, then only allow the philosophers to eat. That means the chopsticks has to be locked so that when both chopsticks are available, then only allow the philosophers to pick it up. So alternate choice of first chopstick means an odd number philosopher should pick up his left chopstick and then right chopstick, whereas even number philosopher should pick up his right chopstick and then left chopsticks. That means when both are available, then only you allow the philosophers to use the chopstick. Till then the chopsticks has to be locked. So this previous algorithm we can improve it using the mutex concept. So mutex we use for locking and unlocking. See, whenever the philosophers are thinking and if they are hungry, see, first of all, all the mutex values is initialized to 1. So whichever the process wants to eat, if they are hungry, they are going to acquire the lock. So mutex values is going to become 0. 0 means no any other process can enter into the critical section. This is a critical section, and once it is locked, the processor, that means the philosopher, can take the left chopstick and right chopstick and start eating. And after finishing, he puts down the left chopstick and right chopstick and then release the lock. So this what bit something improved if you compare with previous algorithm. So another solution we'll see for this problem, solution with semaphore. So this is the algorithm where processes are defined and the various status are defined: left, right, thinking, hungry and eating. So this is the same algorithm, we'll see this. So solution with semaphore, it uses n semaphores and those are in a arrays. Semaphore values we are taken in an array for 5 philosophers and all are initialized to 0, and we also taken the mutex variable for locking and unlocking, and 3 states of philosophers: hungry, eating and thinking. So to synchronize between the processes, these 3 states are very necessary. So the philosopher can only move to eating state if neither neighbor is eating. The philosopher is going to move eating state when his both neighbors are not eating. So the philosopher enters if he wants to eat. Then currently if the philosopher is in a current thinking state, and then if he wants to eat, he is going to execute the take forks function. This method will get executed. Then it will go to the take fork function method, and here first the lock will be acquired. Earlier it will be 0, and then it will acquire the lock using the mutex, and then it is going to change the state to hungry, and then it is going to execute state of I method. It will call this method. So in this method, the state of I of the current process is hungry, and it is going to also check whether its left and right neighbors are eating. So the left neighbor should be not eating, and even the right neighbor should be not eating. Should be not equal to eating means left and right neighbor should be not eating. Then if this condition is true, if the current process is hungry and both the left and right processes are not eating, then that process changes its state to eating and then increments the value of synchronization. That means currently there is a one process eating, and then after taking the forks it will start eating here, and then after eating, so whenever the process is eating, no other process will interrupt it because it is already locked using the mutex. Now when the process finishes its eating, it is going to execute put forks method. So it will call this method. Now in this method it is going to first acquire the lock, then from the eating state it is going to change its state to thinking, and then it is going to execute left and right, means it is going to keep first left chopstick and then right chopstick, and then it is going to unlock. So this algorithm which will solve the synchronization between all these processes, and chopstick will be shared among all the processes equally. See, we'll see same example. So all the processes are initialized to thinking state at the beginning and all are initialized to 0. So whenever the processes wants to eat, they are going to change their state to hungry first, and it is also going to check if the neighbors are not eating, and if the neighbors are not eating, then it is going to change its state to eating state, and then it is going to increment that currently there is one process who is eating, and then when it finishes it is going to make it back to 0 so that other process can start eating. So the next process P4 wants to eat, so the P4 process change its states to hungry, then the P3 process is blocked here. P4 process is blocked here because P3 is still eating here and no other process can interrupt in between. And when the P3 finishes, it changes its state to thinking, and then P4 can get the chance for eating. So this is the solution for dining philosophers problem using semaphore. In the next session, we'll see some new topic. Thank you.